Today we will deep dive into three main areas within distributed databases. The two-phase commit, which is a critical for achieving transaction consistency across multiple database nodes, the quorum concession protocol, an essential approach to managing distributed consistency control, and finally we'll explore the gap theorem implications on consistency and availability, which are often difficult to balance in distributed database systems. By the end of this presentation, we'll have a solid understanding of these key protocols and their real-world applications. Let's begin with a high-level introduction to distributed databases. So, what exactly is a distributed database? At its core, a distributed database is a collection of data spread across multiple computer systems connected via network. These databases are not stored on a single machine, but rather distributed across a range of servers or nodes, which could be in different physical locations, perhaps even across different continents. Now, why is this useful? One of the primary benefits of distributed databases is scalability. With a traditional centralized database, there is a limit to how much data you can store and process efficiently. In contrast, a distributed database allows you to add new servers to network, expanding the system's capacity almost seamlessly. Another key benefit is fault tolerance. With data stored across multiple locations, if one server fails, the system can continue operating by retrieving data from another server. This makes the databases highly resilient and critical for companies like Amazon or Netflix. Their services interrupts could have significant consequences. Imagine a global e-commerce company storing data across regions. By distributing the database, they can ensure quicker response time for users in different parts of the world, reduce latency, and handle high volume of requests more efficiently. Key challenges in distributed databases. While distributed databases offer many advantages, they also bring unique challenges that must be carefully managed. Three of the main challenges are consistency, concurrency, and fault tolerance. First, let's talk about consistency. In distributed database, ensure that all users see the same data at the same time, regardless of where they are accessing it from, can be quite difficult. For example, if a user is in New York, updates are recorded. A user in Tokyo should ideally see that update immediately. This brings us to concurrency, or the management of simultaneous access. In a system where multiple users are accessing and modifying the same data, we need mechanism to prevent where multiple conflict. Otherwise, we might end up with inconsistent data. Finally, fault tolerance is a crucial aspect. Since distributed systems involve multiple nodes, there is a high likelihood that one or more of these nodes will fail at some point. The system needs to handle these failures gracefully so users don't experience disruption. For example, if a user is shopping on e-commerce platform, they should still be able to complete their purchase even if one of the servers handling the catalog or payment information temporarily goes down. Now, what is two-phase commit? Commonly abbreviated as 2PC, this is a protocol widely used in main consistency in distributed transactions. In a distributed database, a transaction may span multiple nodes or servers, and it's essentially that this transaction is either fully completed or fully cancelled to avoid inconsistencies. Imagine, for instance, a bank transaction that involves transferring money between two accounts allocated in separate databases. If this transaction were only partially completed, we could end up with an incorrect imbalance in one or both accounts, which would be a serious error. Two-phase commit solves this problem by using two-step process that involves a coordinator and multiple participants, which are nodes involving in the transaction. The coordinator oversees the transaction and ensures that all participants are either ready to commit or prepared to roll back if necessary. The main purpose of 2PC protocol is to ensure atomicity, meaning the transaction is all or nothing, and consistency across all nodes. The prepare phase of two-phase commit. In this phase, the coordinator initiates the transaction by sending prepare request to each participant. This request essentially asks, "Are you ready to commit this transaction?" Each participant then checks its own state to see if it can safely commit the transaction. If it can send, it sends a yes response back to the coordinator. If it can't, it sends a no. This step is critical because it allows each participant to ensure it has the necessary resource or conditions to commit. Going back to our bank example, in this phase, the coordinator would send a prepare request to both senders and receivers account. The sender's account would check if it has sufficient funds for the transfer, while the receiver's account would check if it can accept the deposit. Only if the both accounts are prepared to proceed will they respond yes, allowing the transaction to move to next phase, the commit phase of 2PC. After all participants respond with yes in prepare phase, the protocol moves to second phase known as the commit phase. In this phase, the coordinator makes the final decision. If all participants responded with yes, indicating they are ready to commit, the coordinator sends a commit message to complete the transaction. However, if even one of the participants respond with no, the coordinator will send an abort message instead. This ensures that the transaction is only finalized if all participants can complete it. In our bank example, if both accounts have agreed, the coordinator sends a commit message finalizing the transfer of funds. However, if one account could not comply, say the sender account didn't have enough funds, the coordinator sends an abort message canceling the transaction. This ensures that both accounts either update fully or not at all, preventing issues like partial transaction where money is debited from sender's account but not credited to receiver's account. Now let us look at the workflow. To illustrate how 2PC works, here is a flowchart of entire process. It begins with coordinators sending a prepare message to all participants who then responds with either yes or no. If all participants reply yes, the coordinator proceeds by sending a commit message, completing the transaction phase across all nodes. However, if even one participant replies with no, the coordinator instead sends an abort message canceling the transaction. This approach guarantees atomicity, meaning that the transaction is either fully executed or fully rolled back. This diagram illustrates how protocol steps in to prevent any partial transaction, which is essential for maintaining integrity of data across multiple nodes. Benefits of 2PC. The 2PC protocol has several advantages that make it invaluable in distributed systems. The most significant benefit is consistency. By ensuring that all participants either commit or abort together, 2PC prevents partial updates, which could otherwise result in data inconsistency. For example, in a bank transfer, this protocol ensures that money is debited from one account, it is credited to other, or the transaction is rolled back entirely if that's not possible. Additionally, 2PC provides fault tolerance to some degree. Even if one node temporarily fails or loses connectivity, 2PC can help recover and complete an abort transaction based on the log and recorded state. This protocol makes distribution system much more reliable, especially for applications like financial systems where transaction accuracy is paramount. Coordinator failure. When we implement the two-phase commit protocol, one of the common issues that can occur is coordinate failure. The coordinator role is a central entity in two-phase commit process. It's responsible for initiating the prepare and commit phase and ultimately deciding if the transaction will be committed or aborted. If the coordinator crashes during this process, participants are left in an uncertain state, often waiting for instruction on whether to commit or abort. Let's go back to our bank example. Suppose the coordinator, which is a central server managing the transaction, goes down right after the participants have responded yes to commit. At this point, each participant is waiting for coordinator's commit message, but with the coordinator offline, they are left without any further instruction. This kind of failure introduces such as uncertainty, as participants don't know if they should go ahead with commit or the rollback transaction. How can we handle the coordinate failure? To handle coordinate failure in 2PC, one common approach is to use timeouts. Here is how this works. Each participant sets a timer after they send their response to the coordinator. If coordinator does not respond with a commit or abort within a certain time frame, participants can detect a failure. Once a failure is detected, participants usually decide to abort the transaction. To prevent any uncertainty. This may sound like imperfect solution because it requires participants to avoid even if they were ready to commit. However, the goal is to maintain a consistent state across all participants, even if that means aborting. Another technique involves logging the state of each transaction. Various systems. Participant failure. Another potential failure scenario in 2PC is when one of the participants fails. This can happen during either the prepare or commit phase, and it can lead to a situation where coordinator doesn't receive a response from one of the node. How can we handle participant failure? When a participant fails, one common method of handling it is retransmitting message. The coordinator can attempt to resend the prepare or commit request a few times to see if the participant responds. However, if the coordinator still doesn't receive a response after several attempts, it will abort the transaction to maintain consistency. This approach ensures that the transaction doesn't remain in a blocked state indefinitely. In some states, participants log each stage of the transaction. So if a participant does recover, it can check its log to determine if it was in the middle of transaction and rejoin or abort accordingly. By implementing the transaction and attempts and timeouts, we add robustness to 2PC. Network partitioning, another critical issue in distributed systems and particularly in uh, protocols like 2PC, is a network partitioning. This occurs when the network itself becomes divided into isolated parts, which means some nodes may be unable to communicate with others. In 2PC, network partitioning can prevent the coordinator from reaching all participants or vice versa. For instance, imagine our banking system where coordinator is located in one region and participants are distributed globally. If the network between the coordinator and the participants in another region goes down temporarily, those participants won't be able to respond to prepare or commit changes. This isolation can lead to situations where some participants have completed the transaction while others have not received the request. Inconsistencies states like this must be avoided as they can lead to data integrity. Handling network partition in 2PC. To handle network partition, we can use combination of timeout and recovery logs. Each participation and coordination keep a log of the transaction state at each state. If a network partition occurs, a participants can rely on these logs to check their state once the partition is over. If a participant did not receive the commit message, it can consult its log to determine if the transaction was aborted or committed. Using timeouts is also crucial in this scenario. If a partition is detected, the coordinator can decide to abort the transaction after a certain waiting period, ensuring that no participant is left in indefinite wait state. Drawbacks: blocking behavior, single point of failure, and lack of availability. Now let's introduce distributed concurrency control. In a distributed system, multiple users or applications may access and modify the same data simultaneously. Managing this concurrency is critical because it prevents the conflict and ensures data consistency across the system. For instance, imagine a library database used by several branches of a city library. Each branch has its own server, but the same catalog is shared across all branches. If a user in one branch wants to borrow a book while another user in different branch is trying to reserve it, a concurrency control mechanism is necessary to handle this access. Without proper control, we could end up with conflicting records where both users are led to believe they have successfully reserved or borrowed the same book. Quorum consensus protocol. One common approach to distributed concurrency control is quorum consensus protocol. In a distributed database, quorum consensus is a protocol used to control access by requiring a minimum number of acknowledgements or quorum from participating nodes before a transaction can proceed. For example, in case of library system, each branch may store a copy of library catalog. When a user tries to reserve a book, the system requires a certain number of branches to confirm the reservation. This quorum represents a majority which helps prevent conflicting actions. By establishing a quorum, we reduce the likelihood of two users reserving the same book at the same time. Quorum consensus also provides fault tolerance. If a few nodes are offline or inaccessible, as long as we still meet the quorum, the transaction can proceed. This protocol is particularly useful in a distributed system because it allows for control and consistent data access even when some nodes are temporarily available. Read and write quorums. In quorum consensus, we have two types quorum requirement, read and write quorum. Each of these determine how many nodes need to confirm an operation before it can complete. A read quorum specifies the number of nodes that need to agree before a read operation is allowed to access the data, while write quorum defines the number of nodes required to approve a write operation. For example, in our library scenario, let's say we set a read quorum of 2 and write quorum of 3. This means that for user to successfully check if a book is available, the system needs agreement from at least two branches. However, if a user wants to reserve a book, we need to write a quorum of 3 branches to confirm reservation. The reason we differentiate between read and write quorum is to manage data consistency without overloading the network. By adjusting these quorums, we can strike a balance between data accuracy and system performance. Quorum consensus protocol flow. When a client, such as library user, wants to read or write data, they send requests to the system. For read request, the client contacts enough to meet the read quorum, retrieves the data, and then merges it to provide a consistent response to the user. For a write request, the client needs to respond from enough nodes to satisfy write quorum, confirming that the data can be safely written. For example, when a library user tries to borrow a book, the system sends a reservation request to multiple branches. If three branches out of five confirm that the reservation, we have met the right quorum, so reservation goes through. If fewer than three branches respond, the transaction fails and user receives a message that the reservation could not be completed. This workflow ensures consistency while still allowing distributed data access. Balancing consistency and availability by adjusting quorum sizes. Choosing the right quorum size is essential for balancing consistency and availability. Generally, if we want to emphasize consistency, we set higher quorum sizes. For example, if we want to ensure that no two users can reserve the same book, we might set the read and write quorum to be more than half of the nodes. This approach can be very reliable but may slow down the system as each transaction requires more confirmation. Advantages of quorum: fault tolerance and distributed control. Challenges with quorum container: increased latency. Achieving consistency across multiple nodes can introduce higher latency, especially during peak usage times when many clients are accessing the distributed system. Operational complexity. Maintaining a quorum-based coordination across a distributed system requires additional infrastructure and operational overhead, which can increase the overall cost of running system. Trading consistency for availability. The CAP theorem. CAP stands for consistency, availability, and partition tolerance, and the theorem states that a distributed system can only achieve two out of three properties at the same time. Consistency means that the all nodes in system see the same data at same time. Availability ensures that every request receives a response, and partition tolerance means the system continues to function even if there is a network partition. Imagine a triangle with each point representing one of these three properties in a distributed system. We are forced to choose between them because it's practically impossible to achieve all three simultaneously. If we prioritize consistency and availability, we may lose partition tolerance. If we prioritize availability and partition tolerance, we may sacrifice consistency. Consistency versus availability. In distributed systems, designers often face trade-off between consistency and availability, depending on application's requirement. For applications where data integrity is critical, like banking system, consistency is prioritized over availability. Example: a banking application would rather deny access temporarily than risk showing users inconsistent account balance. Eventual consistency is data consistency model used in distributed databases where data updates are propagated across network asynchronously. This means that changes may not be immediately visible to all users but will eventually coverage and synchronize over time. Availability. Many modern distributed systems prioritize availability over strict consistency, especially for use cases where responsiveness is critical. Availability-focused systems like DynamoDB Cassandra ensures that users can read write data at any time, even if the data might not fully synchronize across nodes. For instance, in messaging app, user expects to send and receive message without delay, even if some temporary inconsistencies exist. Availability-focused system aim to keep the user experience smooth and uninterrupted, particularly in high-traffic scenarios. Consistency-focused system. On the other hand, consistency-focused systems prioritize strict data accuracy over immediate availability. One example of consistency-focused system is Google, which is used environment where data inconsistency is critical, such as financial record or e-commerce checkout system. In these cases, even minor discrepancies in data could lead to significant error, such as duplicate payment or inconsistent account balances. These systems often sacrifice some availability during network issues to maintain a single rate version of data. By using these techniques like distributed lock and synchronization protocol, consistency-focused systems ensure that users receive accurate information even if that means certain operations are temporarily unavailable during high loads or network disruptions. This approach is essential for applications where data integrity cannot be compromised. Now, availability and consistency. When deciding between consistency and availability, developers and system architects consider several factors based on the application's need and users' experience they want to provide. One key factor is the type of data being managed. For financial transactions, healthcare records, or other data requiring precise accuracy, consistency is prioritized. Imagine an e-commerce platform. During checkout, consistency is critical to avoid double charges, so the system may enforce strong consistency even if that means slowing down the process for accuracy. On the other hand, for applications like social media or streaming, availability is often prioritized. To wrap up, let's recap the major concepts we have covered in this presentation. We started with two-phase commit protocol, which ensures transaction consistency across distributed by using a prepare and commit phase to finalize transactions. This protocol is particularly valuable in scenarios requiring high data accuracy like financial transactions, but it has some drawback, especially when failure occur, potentially leading to blocking and delayed responses. Then we explored our quorum consistency protocol, a method for distributed concurrency control that balances availability and consistency through quorum sizes for read and write operation. By adjusting quorum sizes, systems can manage data consistency without overwhelming resources, making it an effective approach for scenarios where data needs to be both accessible and reliable, like in global applications or content management. Finally, we have discussed Cape theorem, which describes the inherent trade-off in distributed system among consistency, availability, and partisan tolerance. Thank you.